Nashville Systems Programming Day was sponsored by Nashville Software School, offering Web Developer Bootcamp, a 6-month full-time program of intensive hands-on training. NashvilleSoftwareSchool.com.
All right, so this talk started like 2 weeks ago, probably should have been like 2 months ago. Jason and I sat down and talked some brainstorming for this, and he was like, what can we do? And I'm like, I've had this idea for this talk. So what happened was my brother's a lawyer, and he was trying to describe to his friends what I do, and he was like, this dude, my brother, can probably tell you how the internet works down to the electron. And I was very flattered by this, totally not true. I felt like it was something that I probably should know. So now I've had to go know that so I can tell it to you guys. Without further ado, so I'm going to publish these slides after this is over on my Twitter account, Nate Fu, and we're going to talk about this from a conceptual diagram all the way down to the electron. I'm probably going to leave out your most favorite part of the internet, so don't be upset if I leave out like the part that you like the best. Also, I'm on no sleep, so if I get the jitters, it's just deal with it. All right. So let's talk about some definitions real quick. These are all the words you're definitely going to need to know. Super important. Whoa, those are boring. Let's not talk about any of those. Instead, we're going to talk about the 7 layers of the OSI model. This is something network engineers will tell you is also really boring. We don't need to talk about this either. This is what the real internet looks like. So you laugh. Does anybody know what company this is? It's Google, yes. This is taken by me in a data center in Sunnyvale in 2000. These machines, I saw this exact stack of hardware made by Rackable, and you can even see it right here in the corner. This is Rackable Systems in the Computer Museum, the National Computer Museum in Bay Area. And so I don't think they really care if I show this now. It's too old. Now, out of the frame of this is another really cool old thing with the motherboards. You've probably all seen that with the motherboards hanging. That's what the real internet looks like. Not really diagrams and pictures and clouds and stuff. Unfortunately, this is also what the internet looks like. This is the IT closet of this little office that my company rented. And when I was trying to figure out why I couldn't get a port mapped to the switch, I just went down there to try to figure it out myself and saw this and took a picture, and it's kind of crazy. Okay, so big picture, hands in the air. We're going to talk about this from the perspective of your computer to a web server. And probably a dozen or so books can be written about this topic, so I'm going to skip lots of things. And I'm going to pick a really typical situation, which is like your home computer plugged into the internet and pulling up the NashvilleCode.org website. So general concept, computer talks across the internet to a site, asks for a page or some pages, and those get sent back to your browser. The browser shows you those pages. There's a lot of hand waving there, so let's dissect from there. So how does a computer ask for a page and get one back? HTTP, that's Hypertext Transfer Protocol. And by the way, I know a lot of you already know this stuff, but I'm going to try to go through it quickly so we get to the more interesting things later. So the core concept of HTTP is a request is made by you, and a response comes back from the server. A couple different request types: get, post, head are the most common. Option to delete. Get is what we'll be doing a demonstration of in a minute. It's for mostly fetching things. Post is for sending things and also for fetching things and also sending some things. And head is like an informational thing. I'm not going to talk about options and delete. And then response is like the data response back. OK, so this is a typical HTTP request. Can anybody hear, by the way? I want to make sure that this is all working. Yes? OK. Typical HTTP request. You have the first line is the method, the resource requested, and the version. So you see the get method, the slash resources requested, and the HTTP 1.1 version. Each line after that is a key value of headers. So the user agent is like, what a curl or whatever thing. The host is Nashville.org. It will accept back this string, and then it's followed by a character return and a line feed. And if this is a post, there'd be some data and that sort of thing. All right, so on the response, and this is the part that's most valid to our website situation. Similar format as before. You get back confirmation of that version. You get a computer readable code, status code, and then a human readable code. The 200 indicates everything's fine. There's a whole bunch list of those that are really hilarious. You should go look up. I'm a little teapot and all that jazz. And then you get more key value headers, and so you get the link to the content, you get the type of server, the date, a couple other things, followed by a carriage return and a line feed, and then the actual data from the web page itself. Okay, so let's go see what that looks like. Where's my window at? There we go. Okay. I know most of you are familiar with this. I think it's really cool. So let's do here timing. So this is the NashvilleCode.org website. A quick reload of that. Watch all these different resources coming in. You can see 200 status code, everything's cool. That was the method. This is the resource requested. Let's pick this one in particular. You can see the type of data and the size. You can see there's this period of time called DNS resolution. What's that? We'll talk about that in a minute. Connection opening time. Amount of time sent some data, pretty much nil. How long it waited, 64 milliseconds. That is, milliseconds is thousandth of a second. And receiving that data back, 56 milliseconds. And so let's see here. So here's what that code looked like. This is all pretty familiar territory. If we look at the headers, we can see what was sent from my browser, Firefox, to the website. The request was for this host, and I'm on Mozilla, Mac, blah, blah, blah. You guys, some of you may not be able to see this, sorry. What language you can accept and different coding exception or things you can accept. And then the response back, what type of content, the date, stuff we went over before. Okay. We're going to skip the curl demo because this is very similar. All right. Let's see, that tells us like kind of what is happening, but not really where or how or any of that stuff. So we have to go deeper. We're going to see a little bit of this deeper thing. All right, so I mentioned DNS earlier. DNS is the domain name system. This is kind of like the phone book for the internet. It's how the internet knows to look up the address for a website based on the name. So you see like www.nashvillecode.org, and that translates to an IP address, this number. The number is like, to use the postal analogy, that is like the address of your house, whereas like the DNS name, the NashvilleCode.org is like your name, like Nathan Hubbard. I live at X address. So this system is pretty old. It was one of the, well, I wouldn't say it was that early. Anyway, it's hierarchical. There's a top called the root. There's a set of root servers. Those root servers have their own zones they know about. If you hear zone files, that's what that stuff is all about. There's a zone for the com root server serves up all of the like something.com stuff, that whole entire zone. Below that, say it's like, well, let's pick the, org's not on here, google.com. So then there's a Google zone, and it has its own circle that encompasses all of Google and all of its domains. That's at the next level down. And then www.google.com or whatever other, mail.google.com, something like that, is at the third level. So the requests kind of flow down this flow chart. It's distributed, and so when I mentioned distributed, I had Jason review these slides, and he was like, yeah, DNS is not really distributed. And he's totally right. I agree with that. And also, it's also a huge liability for the internet, security problem, all this other stuff. Yes, I completely agree with all that stuff. The thing is, we kind of screwed ourselves with DNS a little bit. It used to be distributed, and then because it is such a lightweight protocol, we now have so much CPU available to us that we can do like literally trillions of DNS lookups from like a single server. So we redistributed, re-centralized it back into, from like thousands and thousands and thousands of servers to like, I mean, literally everybody puts in Google for their, and like OpenDNS, we all use the same, or Comcast. We're like the same 6 ones are used by like almost everybody. So that's not awesome, but yeah, formerly distributed. Yeah, that's much better. And then as the example like of what the DNS system would return, you would look up on NashvilleCode.org. It'd return back this this strange number. Let's talk about what that looks like a little bit. So because of the success of my live demo earlier, I'm going to skip this live demo. But we'll talk through it real quick. So, and you can follow along if you've got your computer open or whatever. Your Mac should have Dig installed on it. Dig is a kind of debugging tool for DNS. You can do a dig plus trace, nashvillecode.org, and I know you probably can't see all this stuff, but I'll just describe it real quick. So normally what happens in a DNS request, if you're like at your home IP or something, your computer will ask what it's configured to ask, which would be like your home router. And your home router probably has a cache on it that might return a number for that name if it knows about it already. If it doesn't, it goes upstream to what it's configured to, which would probably be like, say, Comcast. Comcast also has a cache server, and it returns to you a cache result if it hasn't already seen it. And then if it hasn't seen it, it goes back up. Comcast DNS server actually knows about the root servers and will ask those. So that process goes, hello, root servers, tell me who is authoritative for the .org domain. And you see nashvillecode.org, it's split on the period, and it asks for .org. .org returns, talk to these guys. And then those guys, forgot about the recording mic, those guys return back who is authoritative for Nashville code, which is this ns1.systemdns.com. And then it asks those guys, those particular servers, what the IP is and gets its answer. So it's a couple different steps, and that's where that hierarchical thing comes from. Yeah. Okay, so that tells us how, how to look up where a thing is, but it doesn't really tell us how to get there, what's the map, where are the roads, where are the freeways, that sort of thing. All right, so TCPIP, this is basically the core protocol of the internet, and it's so common that the entire internet is usually just called TCPIP. It didn't used to be that way. So to talk about TCP, we have to understand what role it plays and where it fits. We're going to break it into two parts. Slash breaks it into two parts, but anyway, the TCP handles the reliability, being able to have a connection that's up and reliable. And IP actually handles the delivery part of it. So you can think of it in the postal analogy as the post office, US Postal Service would be the IP. You drop your envelope in the mail, and it may or may not get there, probably will, sometimes does, etc. But if you get that like return receipt going, then you get some reliability. You know that it got there, and if it didn't get there, then you can send another one or call somebody or deal with it. Okay, so to break that down a little bit more, remember that OSI model I was telling you is really boring? It's still boring, but you can boil it down into something much easier to understand called the DoD model, Department of Defense, because they kind of invented the whole internet through DARPA. Little trivia. So basically it boils down to you have the process and application, which would be like Firefox or whatever's running on your computer. You have host-to-host, which is what TCP takes care of. That's the individual machines stack talking to another individual machine stack. You have the IP part, which is the internet. That's the part that goes across all the stuff and comes out over there. And then you have the actual kind of physical network layer stuff, and that's the actual cabling. If you think of it in those four ways, it's way simpler. And if anybody ever asks you what the OSI model is, just tell them this one. It's way easier. Okay, so I also think this is another diagram that helps me understand it. Normally when somebody draws the whole, like, this is what the internet looks like, they draw something similar to the top where it's like you got your server here and you got some like routers in between, you get your server over here, and that kind of tells you a little bit. But I think this even better one tells you how the data flows. You have the two applications, and they're at a level that's just, they only know about each other, talking to each other. You have this next level down, which is the transport. They know about the host part. And you have the internet part, look, all at the same layer. And you have this physical part, again, all at the same layer. And if you want to make connections through this same kind of method up here, it actually transverses all the way down the stack and hits the wire, goes back up to the internet part to like jump to another part of the country, and then back down to whatever link you have. Maybe it goes under the ocean or bounces off satellite or something, and then comes back up to the internet again, layer again, and then back down to physical, and then back up to the application. So I think that, to me, is a little bit easier to understand. Okay, so let's talk about IP right after I do that. Internet protocol. This is the principal communication protocol on the internet, and it's for relaying packets across networks and across network boundaries. A packet is a piece of data. It's not a specific individual type of piece of data. It's just any kind of piece, like grouping of data, just FYI. So I'll talk about 2 or 3 different kinds of packets just for some clarity there. So IP has a routing functionality that enables computers to talk like through entire networks of them and know what path to take. And that is kind of what essentially establishes the internet as what it is. And with IP, each computer has an address, kind of like I have an address for my house. And those packets, the IP packets, include a from and a to, destination and origin. In the example we gave earlier, the origin is probably my IP at home. Hopefully I remember to obscure that. And then the destination of the NashvilleCode.org website. And then the routing functionality is what takes care of how we get from the origin to the destination. That's kind of the map. We'll talk about that in a little bit. And I already talked about this postal system analogy thing. That's really awesome. Okay, so let's talk about IP packets. So this is a super colorful version of what an IP packet looks like. Doesn't actually look like that. It's like lots of ones and zeros. And you can actually see that kind of represented here and there. This is not a TCP packet. This is an IP packet. They're 2 different things. Just to kind of quickly go through this, we've got a version. Usually that's set to 4 unless you're doing IPv6, which would be 6. You get a header length. That tells you how long the entire header is. And this is the header, by the way. The data flows after this, sorry. Usually it's 20 bytes. You've got this TOS field that lets it set things like quality of service for voice over IP, like say like one particular host is more important than another. You can set that stuff. You have the length, which sets how long the actual entire packet is, and it can be as small as 20 bytes and go up to 65K. 20 bytes would be just sending a header. You have an ID. Each packet is given an ID. This is so that if it needs to be cut into pieces and sent out in little different bits, it can be reassembled, and that is the identification for each packet, and so it knows how to reassemble them all. The next little white box is kind of rad. It's called the 0 bit, aka the evil bit, also known as, it's RFC 3541. Hackers are required to set this bit on any packet that is used to attack a target network to make it easier for firewalls to detect. It was an April Fool's joke that made it into the spec. Pretty awesome. It's always 0. So we have the DF is don't fragment. That means that this is a type of packet that can't be fragmented into smaller pieces. And if that happens, then certain error conditions happen. There's more fragments, which means that there is the first packet with lots more pieces to come. The fragment offset, which is an ID that tells it like how far in it is and helps with the reassembly of fragmented packets. There's a TTL, which even though it was originally called time to live, it basically now means how many hops a packet can take. If you've ever been doing like a trace route or a ping or something doesn't come back, a lot of times the time to live is expired. Like if you get into a routing loop, and this is stuff that we can talk about, maybe don't even want to talk about this at all. Yeah, so the next bit is protocol. So that would be like TCP or UDP or dozens of other things that I'm not going to talk about. Then there's a header checksum. This allows it to make sure this header is not corrupt. Just some math on that. Then the IP address that we talked about earlier, the source and the destination, and then options. And options is almost always blank. And it's funny, and I was reading about this, and that's what it says. It says options is almost always blank, except that for my work, that is always set full of stuff. So it actually, in like a real life situation, you actually do lots of interesting things. The thing I do is I set the DSCP bit, which allows you to do things like say, this packet has a certain DSCP bit set, and if it's coming to this network, then route it over here based on what that bit is set to. It just allows you to do really tricky network stuff.
Does that mean like traffic shaping type things?
Yeah, so like in my case, I need to send all my traffic out a certain pair of load balancers, and instead of the network guys having to map like all of my IPs to go out that load balancer and set different routes, I have all the same stuff. I set it in the packet individually on the Linux box, and then it goes, and when it hits the endpoint network gear, it knows to go out that set of load balancers. Okay, so all right, we're going to talk about routing. So routing is the process of selecting the best path. Kind of like the map analogy, you want to know what's the best way to get there. Your phone says recalculating the route or whatever. Same deal. Yes. So routing tables are your most basic type of routing. Your Mac has this, your Raspberry Pi has this, and so does your phone. A routing table basically looks like just a list of this. If you want to go to this IP address, go out this Ethernet interface. If you want to go out this IP address, go out this Wi-Fi interface. If you want to talk to yourself, talk to the loopback device, et cetera. And they're usually very simple. They can get tricky. BGP is what most of the internet uses for exchanging route maps and tables between different pieces of the internet. BGP uses this thing called an AS number. Each one of those is a unique network on the internet, kind of. It's expected to be like a collection of IPs. So like, for example, on Jason's website, or on the Nashville Code website, it started with 66. So at some point, when you're asking the various routing tables across the internet, who can look up this IP address, there should be a table somewhere that says 66. Oh, that's over here. And that's kind of what these things do. They all have like a domain. They know like 66, or in the example of like, what was it, at home internet? It was 8 or 4? I don't remember. A long time ago. Okay. And this is kind of like the stereotypical diagram that we would see that would describe this stuff. You got your computer over here. You got your router at home. You got your cable modem, and then it talks to like the big puffy cloud, and then out to some websites. The thing that I like to add to this is there's probably a lot of wires everywhere, especially in that part. And then there's also routers like all over the place doing different things. Notice the sweet cloud, yeah. Okay, again, I think I want to skip the actual demo of routing because I don't know what internet they use here, but I really like doing trace routes from Comcast because they have super descriptive names for their stuff, and you can really see what it's doing. So in this case, you can see my local host, Notebook Pro, and it's got its own IP address of 10.0.1.1. It connects to my gateway, which is Comcast. I just happen to know that. There's no DNS entry for that looks up. Oops. All right. Next is this Comcast IP thing on Blair Boulevard. What that probably indicates is not too far from my house, a few miles. There's some initial site that it goes to. Then it goes to Goodlettsville, Tennessee, Marietta, Georgia, and then I don't even know because it doesn't really come back as anything. Maybe top secret. I have no idea. Maybe that's where our packets are sniffed and recorded. I don't know. Yeah. That's what 3 question marks means recorded. Just 2 is just sniffed. Yeah. Anyway, just kidding. So then it goes to, and you notice it goes to a completely different internet company. Like it's Comcast up here, and then it hits this Cogent code. Cogent is a large bandwidth provider. Lots of trace routes and stuff go across Cogent's routes and maps and stuff. So you can see that goes. See that ATLO2? A very common naming scheme in networking is to, unlike Comcast actually, is to name it the airport code. So who wants to tell me where we're going next? We got ATL, and then ATL again, and then ORD, which is, yep, thank you, Chicago. And then we've got, for extra credit, YYZ, which I had to look up. Yes, Toronto, yes. Yeah, I had to look that up, man. Anyway, and then it hits this other IP that doesn't really have a reverse lookup, but that's another probably the gateway before it gets to the final destination, which is this.
For like our website?
Yeah.
So I have no idea where this website is, obviously.
It's in Canada. Yeah. 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 If you look up the ORS systemdns.com, their service is Canadian, I guess. Yeah, exactly where was it? Where did you think it was? Yeah, it's on the cloud. Like,
What cloud are you serving? I don't know. Bob's Discount Hosting.
Yes. Okay. Okay, so we talked about routing. We're going to talk about TCP a little bit. We talked about it being a reliable way to get internet information. It also provides an ordered way of getting information. So TCP divides all the packets up into even smaller bytes and sends it in a way that it can come across ordered so that your machine can reassemble it correctly. It also error checks that and provides source and destination ports. So like if you ever look, you're connecting to like port 80 on a web server. That's kind of what that stuff means. And this flow chart is a little crazy. So we're going to do like a little talking about it in a second. Okay, so this is a TCP header. Kind of similar to what we saw before. This, again, rides on top of IP. So just be aware that the features of IP come with this. They're just two different technologies. So you've got a source port, which would be like what you're initially connecting from. All computers have, well, not all computers, but any computer running a TCP stack's got a certain number of ports, usually 65,000. And when it makes an outbound connection to a website, which should be like port 80, it does it via usually a random port or maybe the next sequential port outbound. So that's the source port. It's kind of like the from and the to. A sequence number, that's so that reassembly can happen. Acknowledgement number, that is to acknowledge that things have happened. And a little bit about that. Sequence number, actually. If the sequence number is a SYN type packet, we'll talk about that in just a sec, then that is the first sequence, first bit or byte in the sequence, or first packet in the TCP sequence. If that SYN flag is clear or 0, which again, we'll talk about that in a second, then it's the next one. So what that means is a SYN is sent to initiate a connection. And if that flag is set, then it's the first one. And if that flag is not set, then it's the following ones. That's what that means. So let's see, down here, we've got our data offset. This talks about the size of the TCP header. And then we've got all these flags. See all these funny up and down letters? So the ones that we're really concerned with in describing this today is this one that's SYN, this one that's ACK, this one that's FIN. We're going to talk about those. The window size is the size of the receive window. What that means is the number of window size units that the sender has agreed to and is willing to receive. And there's a checksum on it to make sure this is all valid. And there's an urgent pointer. I'm not really sure what I would use that for, but I felt like it was important to cover it since it says urgent. And then we've got some various options that you can set. I'm not going to get into that. OK, so let's talk about that conversation that TCP has. And again, with the water. Hang on one second. I need like a little drip. Anyway. OK, so first off, we start with the SYN. I was saying that the SYN is the initiator of a conversation. So in the case we were talking about earlier of like your home computer talking to the Nashville Code website, your home computer would send a SYN packet and go into the SYN sent state. It sends it to that remote host. The remote host and this is basically what it's saying. You want to talk? Yeah, sure. Here's my port and a random sequence number. The reason it's random is that it used to be sequential, and then people figured out like what the ordering was and were able to like get into your TCP conversation. So now it's like randomized. And then a SYN and an ACK is sent back from the server to the client saying, yes, I would like to talk. And here's another random sequence number. And then an ACK is sent from the client back to the server saying, yes, this is going to be sweet. And here is your random number +1, and that's the next start of the sequence. OK, so now at this point we're in the established state. What this means is awesome stuff happens. We send the data, and all this jazz goes on. You get your YouTube, you get your image, whatever. You get that image. It just came across over an established TCP connection to my computer. All right, and then I went about trying to describe the teardown in the same way and got like actually super confused with myself. So I just grabbed a diagram, and we're going to step through that because I think that's a little easier. So we go to end the connection. There's the bring up, the established connection, and an exchange of data, and then the ending of the connection. So we go from the established state and say your client usually initiates this end, although it can happen all kinds of different ways, but we're gonna use this for example. So your client is like, cool, I've got the data I needed, we can now be done. And it sends this fin packet to the server. The server acknowledges and says, sure, I'm done talking. Or sorry, it says, sure, okay, I can close. And then it also initiates a close back to the client. Says, yes, I want to be done too. And then the client initiates back and acts saying, okay, cool, I can close you. And if you've done any if your website's ever been bombed, you will have seen, if you look at the output of your netstat, and this may be a little out of my gore to talk about this, but you'll see lots of things waiting in time wait. And I've seen this before in various stages of breakage in my career of things being in all these different spots. So this is kind of a neat diagram. I almost want to print it and put it somewhere because I forget this so often. I'm always like, yeah, it's in time wait. What's that one do again? Anyway, and time wait is actually not awesome. That's the one that has a 4-minute max, and usually you have to change your kernel to lower it so it doesn't blow your computer up, because if somebody connects to your website 65,000 times, time wait actually will not let the computer recycle that old port until it's completely closed. So somebody can actually DOS, this is part of the DOS attack, denial of service attack, to hit your computer so fast that it can't close up these connections and then can therefore no longer open a new one to respond back. All right, so we got TCP established, but how does my Mac talk that? That whole thing with all the bits and bytes. We got how it gets there with the packets and stuff, but how does my Mac actually do that on my computer or whatever? So it's with lots of people agreeing on standards. So the one we're going to talk about is IEEE 802. It's just a spec, but it's a really large one. It covers a lot of things that you're familiar with. Ethernet, which is the little, well, I don't have one here. I was going to do show and tell. Have you seen an Ethernet cable before? Anyway, I'm just. Yes, I'm mostly joking. I think you guys would probably think. I forgot to put it in my back pocket and be funny. Anyway, so it covers Ethernet. It also covers Wi-Fi, which is what I'm using. It covers bridging, a couple other things, actually hundreds of other things. But we're going to stick with Ethernet so we don't die of boredom while I'm up here talking. Just for some trivia there, this spec deals with networks carrying variable size packets. Cell relay networks like your cell phone, the packets are uniform in size. And then there's other types of network where the packets are uniform size, but the data is divided up by time. So it doesn't talk about any of that. And there's some speculation as what the number means. Some people think it was because this spec was ratified in 1982, but most people agree that it was because the 802 is the next number available. Okay, so we're going to talk about Ethernet and local networks. So Ethernet, this is the RJ45 thing we were talking about earlier when I was trying to be funny. Ethernet is for the most part for dealing with local networks and maybe metro networks and that sort of thing. It is so common that it has replaced pretty much every other wired LAN technology. I was told not to mention Token Ring, but I have to. Token Ring was one of them. It's been replaced. FDDI and ArcNet, some of these other really weird, obscure things that pretty much are no longer in use. Yeah. So Ethernet divides data into streams of smaller data called frames. Each frame contains, big surprise, a source and a destination address. Error checking data so that damaged data can be detected and retransmitted. And each Ethernet station, in my Mac or in this case, whatever this computer is, has its own 48-bit address. That's what the MAC address that you've probably heard of that before. Stands for Media Access Control. I actually had to look that up. I've said it for so long that I couldn't remember what. I was like, what does MAC stand for? God. Anyway, Media Access Control apparently. Those are used to specify from hardware to hardware what the addresses are, just like the analogy earlier from my home address to someone else's home address. Ethernet establishes link level communications between two physical devices. So this is And we're only talking about Ethernet here. This is not what the whole internet runs on, but it's what a large part of it runs on. And this is what does the actual connection between two machines, or two routers, or your cable modem and your Linksys router, or whatever. So it's also designed for use on, we talked about, oh yeah, hey, I should hit the little button there. There we go. It's also for use on shared media. And when I say shared media, what I mean is like many connections can happen on a single cable. That used to not be the case with older standards, why they don't exist anymore. All the information is sent by one computer and received by all of them. Even if that's not intended, even if it's just intended for one destination, it goes to all the things on that wire. And there's a whole bunch of different standards, lots of them, like hundreds and hundreds of them. So ones you may be familiar with and ones that we'll kind of go over a little bit. 10BASE-T, that's over like a Cat5 cable that we're looking at there. It looks very familiar with that same RJ45 connector. 100BASE-TX, which is like the 100BASE-T that you may have it in your home in between your Linksys and your cable modem. Yep. And then Gigabit 1000BASE-T, which you hopefully have that between other things because that's way faster and cooler. Other things that are Internet or Ethernet-E are Ethernet over fiber optics, and 10BASE-2 over coax. And I only mention that because it's horrible but also cool at the same time. At one point in my life was helping build a computer lab, and the cool thing about using coax was that you get these little T connectors, and so you run one piece of coax, and for every computer, so instead of running like a huge bundle of wires, which is what we're all familiar with now, you run one piece of coax, and you put a T connector on it, and connect that down to the computer, and you're done. You run it, and it's that same one piece of coax that goes across the whole room. You just put T connectors in it, and I mean you have to break it up into sections, but that was really nice. It's also super slow, 2 megabits. Okay, so the thing we plugged into there earlier was called the network, the NIC, or the network interface controller. This is the essential piece of gear you need to talk on a network. Other names for it: network adapter, NIC card, which is really funny because it stands for network interface controller. And I guess you say network interface controller card. Anyway, it's not really in card form for like a long time. That's a card form version. And it even has a coax connector for 10BASE-2 on it. See the little twisty thingy? That's an ISA card from like a jillion years ago. It's a LAN adapter, modem, and host adapter. But host adapter is usually used for fiber channel when you're talking about like storage networks or something. Okay, other Ethernet gear. Click. There we go. A hub / repeater. So anybody in here remember hubs? Yeah, okay, good.
So like there was a special kind of cable you had to use, the backwards?
Yeah, the backwards cable, the like swap, the crossover cable, yeah. That's still like sometimes used out there.
Yeah, you can use crossover cable to connect two computers together without a switch between.
Right, on modern machines, they will do that for you.
Yes.
Because people are like, I have to have a special cable for this?
Yeah. Some NICs will,
Yeah.
Nice.
And you can't go, you can't really go to like Best Buy and say, I need a cable where the ends are like turned over, and yeah, you got to make it so it's a whole thing. Yeah, all right. So in a hub, every packet is sent to every port. On the repeater, hub and repeater is a very similar thing. So bandwidth and security problems are not addressed because every port gets every packet. Total throughput of the whole thing is limited to whatever the speed of a single link is, and all links need to be the same to operate. All links must operate at the same speed. Nobody really has those anymore. I actually remember recently looking up to see if I could buy a hub, and I could find one. It was like $900. I don't understand that. Like, maybe. Yeah, I don't get it. Yeah, more ports. Oh yeah, I guess I could click. Anyway, yeah, and the hub is what provided the initial star topology that. Because usually, initially it was two network cards connecting directly to each other. Then they're like, well, I don't want to just do that. I want to share this cable. So they stick a hub in between and allow it to talk to more. And that kind of gave you the ability to have your computer connected to one thing, a hub in the middle. And that would be connected out to various other pieces of gear. A switch is what we almost all have now. Also can be talked about as a bridge. Packets are typically delivered only to the port that they're intended for physically. So like, well, this is Wi-Fi, so this doesn't really apply, but in a switched Ethernet, for example, Let's see what my next click is. Yes. Yeah, it helps you isolate the physical from the data. So it does inspection on the packet and looks to see if the header, what the header is destined for, and then routes it to the appropriate location physically on the network. That way, the cable, the bandwidth is preserved, and you don't get crosstalk. With a hub, not crosstalk, but collisions. When they're all talking at the same time on a hub, the packets can actually collide and die, and for lack of better description, and you get loss of bandwidth and other things. And I can remember on my old hub many, many years ago, it had a little red light for collisions, and whenever I would download something off of, it wasn't Comcast, at home, real fast, that little light would just glow real bright because it was colliding and killing my bandwidth. So that's eliminated with the switch. And because the collision domain is eliminated, those connections, it means that the link bandwidth is also can be used for 2 devices on the segment. Boy, I wrote that note really terribly. Well, anyway, collision detection means that you get full bandwidth. So let's do a little packet capture demo. If you've never messed around with capturing packets, I highly recommend it. I pre-captured this because I thought there might be a problem and I wanted to make sure there wasn't one. But we're just going to quickly go over what it looks like because this talks about pretty much all the conversation that we've talked about up to now. It talks about TCP, HTTP, talks about IP and Ethernet frames and all that jazz. So we're going to kind of step through one of these packets. So if you look at this conversation, you can see, so this was just me requesting with curl just the first page of NashvilleCode.org, and that's all this stuff happened. You can see the SYN-ACK and the ACK that opened the connection. You can see where that came from and where it went to. And let's look at what those look like. We're looking at one now, okay. You can see, let's see here. Yeah, can you guys, can you read this at all, or is it too small? Kind of readable? Okay, well, I'll talk about it a little bit. So the source port here, this is at the TCP level, source port 58332, destination port 80. TCP segment link 0 because it's the first one. Window size value 65K. Blah, blah. Some of this stuff is just Wireshark printing out things. And again, I definitely suggest you download Wireshark. It kind of can be a trial to set up for the uninitiated, but it's definitely worth looking at this stuff because it's really neat. Remember that urgent pointer? Not urgent. So here's some of the options that were set. Really, none of that stuff's interesting. I should be reading here so I can actually see it. Oh yeah, there's our timestamp value. And then if we kind of go, so that's the TCP packet part. So let's look at the IP packet part. So here's our version 4, IPv4 internet, that's what that means. Header is 20 bytes long. I don't have any interesting bytes set, although you can see that DSCP bit that I was talking about right there earlier. I use that. And these other ones are used by lots of different people. You can see that don't fragment bit. You can see the more fragments, all that jazz. Time to live is 64, so it can actually do 64 hops, although my computer allows that. That is most likely not going to be honored by all of the other pieces of gear in between, who usually do like 15 or maybe 30. 64 is pretty long. And then you see your source address 10019. That's this computer here, and your destination address right there, which is Jason, the NashvilleCode.org website. And then at the Ethernet layer, we see my computer talking to. And so this was captured on, actually not this machine, it was captured on a machine physically plugged into my network. So this is it talking to my switch in my house. So you see this crazy string 01B63 blah, blah, blah. Actually, if you look up 001B63, like all Apple stuff looks like that. It starts with that. And there's even a database where you can look up, if you want to figure out what piece of equipment sent something, on your network, you can actually look up those first couple things, and it will most likely tell you what kind of piece of gear that is. So you can see this destination and source, a couple of little things set, pretty simple stuff. And then other parts of this frame talk about arrival time. Here's a Wireshark thing for coloring it. Anyway, there's a lot of stuff in here. definitely worth exploring these things on your own more later. In the case of the actual downloaded resource that we got earlier, you can see the same text that we saw, this get request. Here it is with the requesting / there's the version. There's all the same things we saw earlier, but we're seeing this by capturing the actual raw packets themselves. And you can see what was returned back, and it doesn't give me the whole thing. That response was 5 total Ethernet frames on my local network. And then just actually to follow that conversation out, you can see the ACK, the fin, and the closeout sequence there at the end as well. Shift Command F. Oh, okay. So, but then what happens? So we have to go deeper. So now we're going to talk about the physical stuff, the actual network across your cabling and that sort of thing. And we're going to pick Gigabit Ethernet because that is probably the topic that would be most applicable to what we all do, or maybe what's in your house or whatever. And it's all kind of variations of this, so we'll just kind of dive into it. The physical layer is probably the most complex layer of the whole thing because it deals not just with, like the other layers have really well-defined specs, I think is a better way to say that, and everybody speaks them, whereas the physical layer is not quite so. You know how like, well, a good example is USB is a physical specification. Yeah, so is infrared and Wi-Fi and the CAN bus in your car, and DSL as a protocol, as a whole system, and also 100-base-T Ethernet. Those are all physical layer specifications. So there's just thousands and thousands of these, and they get really complex. It deals with the shape of a connector, the modulation scheme, and when I say modulation scheme, I mean like how the data is spoken over the wire, and the frequencies. And that has to deal with not just specifically like radio, but I mean the speed at which the data is sent. Okay, so Gigabit Ethernet, 1000-base-T. Remember the IEEE 802. This is 802 part 3AB. Looks like this. It is made from copper, which is an excellent conductor. Why does it say copper specifically? Because we all probably expect that wires are made from wire, right? But it says copper because copper is part of this standard. Unlike you could have a wire made out of plastic, or it could be talking about air, like Wi-Fi, right? So that's just for some sort of trivia. That's what they mean when they say it's copper. It seems self-intuitive, but that's what they mean. It's an excellent conductor. It's unshielded. Coax, like your cable modem connection at your house, right? If you've ever cut one of those open, which I'm sure everybody has when they were like, I don't like my TV anymore, and you look inside it, if you look inside that, it's got this like kind of foil metal shield, and then there's like a little buffer and then a central core. Well, Gigabit Ethernet does not have that. Instead, it has a twisted cable. And the twisted cable is really neat. It was invented by, the concept of using a twisted cable was invented by Alexander Graham Bell. When you twist those cables, the electrical properties change and no insulation is required. This is kind of what the cables look like, and you can even see the little colors. I always mess it up whenever I'm making cables. It sounds like you probably don't, would be my guess. You sound like you shaking your head.
That level.
Okay, all right. This diagram kind of shows, so you've got your plastic, if you've ever cut open one of these cables, you see it's got this plastic piece, and there's a whole bunch of wires, and sometimes there's like a little cross in between or something to kind of separate them out a little bit, and they're usually twisted up in little bundles. That twisting action means that data can be sent, and it doesn't radiate as much energy and doesn't accept as much energy. When I say energy, I'm talking about electromagnetic radiation generated by the electrons flowing across this cable. And we'll talk about that in depth a little bit more in a second, but just this is what it looks like. Max length 100 meters or 330 feet. After that, all bets for the spec are off. You can try to make it that length. It may have less, or maybe bad things would happen, I don't know. And then it uses PAM5, which is 5-level pulse amplitude modulation. We'll talk about that in a second. And it uses trellis coding. This is how the signal is encoded at a digital level. sounded like that guy from The Matrix, the representation of your digital self. Enunciate those words, really. Anyway, pulse amplitude modulation means that the data is represented as the amplitude of the transmission instead of like other methods, maybe by slight time or frequency. So the pulse is larger and smaller to indicate bits. So, yep, encoded in that. Double polarity means that it goes both ways. It goes on top, positive and negative amplitude. And level 5 means there are 5 different levels of amplitude available to detect. And you can see in this graph right here, it goes, it's kind of, this is a great little representation of what it looks like. Each one of those little slices is 8 nanoseconds. And the height of it, you know, to get 5, it starts at -2 and goes up to +2 for 5 total. 4 of those bits, let's see, yeah, whoops, whoa. That's pretty good at a systems programming talk to have that. Well, maybe somebody can cover that later. The 4 different levels of signal represent 2 bits, and the 5th level actually represents forward error correction. And when you see the 0 to +2, that if I just have to say this in case somebody out there knows this and wants to correct me, that actually doesn't mean +2 electrical voltage. It means it's actually those are just the counting of the levels, not how much electrical voltage is applied. It's not more than the wire can handle up to +2. It's like just what the wire can handle and then a level half of the what it can handle, 0, -half of that, and negative full. And again, 8 nanoseconds is what each slice is on Gigabit Ethernet. Okay, trellis coded modulation. They called it that because it looks like the trellis in a garden. It's a modulation scheme which allows highly efficient transmission of information over bandwidth limited channels. If you remember the modem days, TCM became used around the 300, 1200 baud time frame. I don't really know exactly when, but if you remember that time frame, we were at like 1200 baud for forever. And then all of a sudden it went 2400, like 9600, 14.4, 28.8, 96, and all this. It just went way up really quick, and it's because of this stuff. Trellis coding works on a sliding window. So each one of those 8 nanosecond slices is a 4-bit. This representation of 4 bits right here. You can kind of see that 0, 0, 0, 1, 10, 11. Okay, questions about this? I don't know this super well, so if there are questions, we may have to figure it out as a group with Google. I don't know. But any questions? All right, great. Gigi continued. So that 8 nanosecond slice means that 1000 base T Gigi runs at 125 megabaud. And I wanted to say megabaud because that's such a cool word to say. Megabaud baseband signaling. What that means is 125 million pulses per second. So if you have 8 wires in your Ethernet cable running at 125 million pulses per second, you get Gigi. You get 1000 megabits of bandwidth. If you do the math on that 8 nanosecond division, that also is that 125 megabit number. Kind of neat. But how does it do that? We have to go even deeper. So we're going to talk about copper and why electrons move across copper. Copper is an amazing substance. It has 29 protons, 29 electrons. If you remember from your science class about the electron shell, the atom has its nucleus, and there are certain levels of electrons that go around it. In the case of copper, there are 4. The first shell, which can accept a max of 2, has 2 in it. The second shell, which can accept a max of 8, has 8 in it. The third shell accepts a max of 18, and it has all 18 in it. So all 3 of those first shells of copper are fully populated with electrons. The last outer shell only has 1. And because there's only 1 in that 4th shell, it can just jump around very easily and become detached. Now, this is actually pretty common in most metals, but in copper especially so. So I'm going to have to read a little bit here because some of this gets a little crazy. But in the metal lattice of a solid chunk of metal, electrons are allowed to roam free in that metal lattice. If you've got an electron, a wire of copper, electrons can roam all throughout it, no problem. That spare electron, all through the whole thing. They move at a speed of 1 millimeter per second, which is way slower than what we think of when we plug something in and it shocks us instantaneously, right? Or when we say, oh, well, my stuff moves at the speed of light, blah, blah, blah. Well, that's just what speed the electrons move. The electromagnetic wave moves at near the speed of light. And that is what we are seeing when we're moving electrons across that, or when we're putting energy into one end of the wire and getting it out of another. We're seeing that electron wave flux across. So let's see here. I have more cool stuff to read. Even with no electric field, the electrons are moving about randomly due to thermal energy, like heat. Actually, I think I read all that. Wow, sweet. I guess staying up till 4 working on this actually paid off. Anyway, so what makes electricity go in one end of a wire and out the other is this availability of the electrons to roam freely in this piece of copper. But in order for that to actually happen, a difference has to be applied from one end to the other. So if you have a raised voltage or raised a number of electrons here, or an electromagnetic field on this side, energy will flow to the other side. And it flows in the direction of electron flow generally when you're talking about a diagram. So it's kind of weird. If you apply a positive voltage, the electrons actually flow energy flows both ways. So it's kind of the direction that you want the energy to go in. That's when it's drawn in a diagram. You know, you see the little plus and it kind of goes around like this. The large side of the plus is the positive, the small is the negative. You apply to the positive side, the positive goes around the circle to the other side like this. And I know this should probably be a diagram. I just didn't have that. So anyway, so that's why electrons flow across copper so well and just metals in general. Piece of trivia, I'm going to ask this question. Silicon is a metal. It's conductive. Why are they not made out of silicon? We make chips out of silicon. Well, it's only semiconductive. It doesn't really flow that well. And I'm not going to get into how to build transistors because that is super crazy out of my scope for this talk. But that's why it's called a semiconductor. Semiconductors are made out of a semiconductive material. Anyway, and for comparison to copper, lightning is the thing that you can very easily see. In a lightning discharge, the electric field is so high from one end to the other that even those bound electrons that we talk about that are in those electron shells, like that are in copper that roam free, those are ripped right out of the atoms and turned into an ionizing gas and creates plasma, and it can actually flow across that piece of plasma because the energy difference is so incredible. All right, let's see, click. Okay, you love electrons, and here's why. They are responsible for magnetism, electromagnetic interference, and radio, electricity, and lightning. I highly recommend you read more about electrons because they are awesome little boogers. Also, they are responsible for creating radio waves, and I thought about going into this a little bit, but it gets even more crazier, I think, than just talking about Ethernet and copper. Yeah, really crazy. Anyway, and then I wanted to give a shout out to my homeboy fiber optics because also a large part of the internet goes across fiber optics. That uses light instead of electric pulses. And just for some quick stuff about that, fiber optics has crazy advantages over copper. A single optical fiber can carry 3 million full duplex calls or 90,000 TV channels, which is pretty awesome. That's from Wikipedia. I don't really know how old that is, but it seems like it just keeps creeping up every time you read that page. It's immune to electromagnetic interference. You can run it super long distances. So this is what they put under the ocean when they run cables to other countries. Because it can deal with that super long length. The light goes in the piece of plastic. Remember I said plastic media earlier? Plastic. Or maybe glass. So I guess glass could be another one. The light goes in there and instantly arrives at the other side, no interference. And yeah, and even a nuclear bomb could go off and it wouldn't affect fiber optics, which is pretty awesome. What's that? Yeah, well, yeah. I mean, like the fire and stuff raining from the sky would probably like really mess it up. But and then, yeah, dude, yes, yeah, that actually is bad. And then also, it's an electrical insulator, so. Unlike copper, like you can actually get electrocuted by screwing around with this stuff, but not so with fiber. And also, you probably know people steal copper out of houses that are left that have the front door open for more than 5 minutes, and that's not really a thing with fiber. The end. So my goal here was to teach you that thing about, so that you can now say, I know how the internet works all the way down to the Electron. And for further reading, I suggest you check this stuff out. I'm going to publish this to my Twitter account in a few minutes. Another really cool thing, I don't know, this looks crazy, but I posted this as a gist on GitHub, and it's in that last set of links. This is a script you can tell curl to do, which will tell you all kinds of really cool timing information about what happens in a TCP or HTTP connection. You can see lots of neat stuff there. I just wanted to show that. That's it. Yeah, thank you.